So 2 facilities were funded through a competitive process. The Australian government, when deciding to build up the capacity for patent approval in Australia, put out a call for laboratories to submit an application to upgrade the facility to undertake the testing, and our facility and Manly Hydraulics was selected. When we initially put our funding request up, we only wanted to do water, and then we were told that no one else had put up their hand to do all the hard stuff, which is all the electrical and vibration and dust. And so we reluctantly put our hand up to do that, and it's been quite a challenge because we're sort of guinea pigs in this whole exercise, where we've had to understand how to undertake these tests, source equipment from overseas, and so it's been quite challenging. Our understanding is that the overall testing requirements that we undertake, there's only one other laboratory in the world that does it, so it's quite a unique facility. The accreditation process was quite challenging. Over 900 documents was produced in order for us to be approved to undertake the testing. So for every test, there might be 3 or 4 standards, international standards that we've got to work to. And once we got our NADA accreditation, I'm not sure what the equivalent here is in New Zealand, but it's EINS, yeah, okay. Yeah, right. So once we got our NADA accreditation, we then could apply for patent approval and verifying authority from the government, and that's Alex's organisation that appoints the patent and verifying authorities. In terms of the process, a manufacturer would first of all submit an application form to NMI, get an application number. They would then, if they've got information on previous testing, so some of the manufacturers had testing done overseas to OIML, the R49, which someone raised a question about. So there might be some pre-existing testing results that might apply to the patent approval tests. So NMI might accept those test results, but they'll only accept them if they're undertaken at an independent laboratory. They can't be undertaken at the manufacturer's facility. So they have to be undertaken at an independent laboratory. So what we do, we look at the information provided by the manufacturer, and then we work up a program between the facility and the National Measurement Institute. And from there, we then look at undertaking the tests. During the testing program, there's essentially 2 components. There's a performance, which is accuracy flow testing, and then there's all the disturbance, the environmental tests, and influence tests. And we might have instances where some settings on the meters might need to be changed, or some configurations in terms of pipework might need to be negotiated, and there'll be some consultation with us and the manufacturer. And we might even need to talk to our NMI about what do we do about this particular test. In parallel with this, there's an endurance field test, which is equivalent to 100 hours at the Q3 flow rate. So that's sort of at the nominal flow rate for the meter. And that can be done in the field, and the manufacturer can organise that. So they'd send out 3 meters out in the field and let them allow them to be operated for a duration. It's not a fixed duration, but provided they meet the 1,000 hours at the Q3. So this is equivalent volume of 1,000 hours at the Q3 flow rate. And obviously record some of the environmental conditions, so temperature and humidity, and the type of water quality that's passing through the meters. So once that's happened, they send the meters back to the facility. We test them again to see if they're okay. The reports get submitted to NMI, and a patent certificate, approval certificate is issued. Sometimes they may only issue an interim certificate, so there might be some things that aren't completed, and that's usually the endurance tests. But they've got a certain period to complete that. So what are the key things that we seek from the manufacturers is the bottom flow rate and the nominal flow rate, which is Q3. And in most cases, they've got this information from R49 testing, which is the OIML testing. And essentially, it's generally an error curve, but with the OIML R49 requirements, they allow the Q1 flow rate to drop down to 5%. For NMI, we hold 2.5% as the maximum pistol error for the entire range. So that's the difference between the R49, so this is the European testing or the OIML testing, and the NMI testing. So we've got to stick within 2.5, whereas OIML allows you to drop down to 5 between Q1 and Q2, which isn't shown here. But also they operate within plus or minus 2%. So there's some slight differences with errors, permissible errors. The other thing is that we need to look at is most of the manufacturers have family meters, and they range from anywhere from 40 up to 1200 mil. We generally go up to 300 in our facility, but so there might be 5, 6, 7, 8 different sizes, and we have to decide which of those meter sizes we test. And generally we look at issues to do around the geometrical design. So if there's no geometrical differences across the family, so if we're increasing in ratio and there's no changes in the components, we might get away with testing 3 metres out of the family. And with the environmental test, so that's electrical testing, the dust testing, and we generally test the smallest metre in the family, so that might be a 50 mil metre. So here are the two categories of testing. All the meters, so mechanical and power meters, have to go through the first lot, which is essentially flow tests with a range of disturbances and water quality. And then there's the environmental tests, which have influences. So there's power, temperature, vibration, electromagnetic susceptibility. So in terms of what we've done in our laboratory, we've got all this equipment here that we've essentially upgraded the facility with, and that's an environmental chamber room, electromagnetic immunity chamber, or it's actually test unit, EMC, which is electromagnetic compatibility testing, a shaker or vibration system, dust for IP assessment. We've got reference measurements, gravimetric tanks. We've got a quality rig, so that's to test the meters under different water quality parameters. Hydrostatic testing and various pumps and pipe work. That was what we had to put into our facility. Our overall capacity increased from about half of that 250 up to 520 litres a second, and our least uncertainty is around 0.1%. So just to go through some of the equipment, this is our environmental chamber. We can go down to about minus 30 or minus 40. We're not quite sure at the moment. We've gone down to minus 30. And we can go up to 60 plus and control the humidity for any of those, or for at least the heat temperature conditions. So we do 3 tests in the laboratory. There's a cold test and there are 2 heat tests. And one of the heat tests is called a damp heat test. It runs over 48 hours or 2 days. And we cycle between 25 degrees and 55 degrees during that period. And the tricky part with this test is that we've got to hold the humidity at around 95%, a little bit over sometimes, and a little bit below sometimes. So we're continually getting condensation taking place. This is the the electromagnetic immunity chamber. So it's a GTEM. we test essentially the impact of radio frequencies or electromagnetic frequencies from radio towers, mobile phone towers, television towers. And we go from, you probably can't read there, from 10 megahertz up to 6 gigahertz. So we thought we're still able to cover some of the new frequency ranges that are coming through for mobile phones. So I think they're nearly up to 5 gig. So we've got 4G already in Australia, and they're talking about going up to 5G. And so what we do with this particular test is that we run through, I don't know, it might be maybe 200 or 300 different frequencies. And we start at 20 megahertz, and we can go up to 6 gigahertz. And each step, the frequency goes up by 1%, and we have to monitor the meter whilst we're testing. So we've got cameras on them, we've got pulse outputs collections on them, and for each step we need to see if the meter is still operating for those frequencies. This is the IP rating, the dust chamber. What we do here is that we apply a small vacuum to the chamber we want to rate, and it's a small vacuum. It's only minus 2 kPa, which is 200 mil of water suction. And we then circulate a talcum powder or a particular dust of a certain grading. And before we actually start the test, we've got to get the humidity down below 30%, so the powder doesn't clump up during the test. So this runs for a whole day, and we cycle between 25 degrees and 65 degrees, so we're getting some expansion and contraction taking place. And we test the meter before and after to see if its accuracy has changed. So this is the IP rating chart. 6 is down here, which is for devices that don't allow dust to come into the chamber. And the 8 is when we put the meter below into a water column or a tank, at least 1 metre below for a period of 2 hours, I think, 1 or 2 hours, I can't remember which one it is. And that allows us to give the meter an IP rating of 68. That was very important in Australia because of the environment we've got, and also the fact that some of these meters may actually be in pits which might get flooded from time to time for whatever reason. So it's an important assessment of the meter. And this is the really hard one, this impact test. So we lift one end of the meter 50 mil and just let it drop, and we test the meter before and after. And it was really intended for making sure that meters that are in transport can cope with a bit of bumping in the transport mode. So vibration. So there's a vibration test. It's not a very aggressive test, and it's really compulsory for meters that are used on a mobile system. So if you're driving around and testing meters on the back of a trailer or something like that, that's really what it's intended for. NMI are considering whether they should make it compulsory. So it'll handle things to do with transport and bumping around, vibration. So you might get a bit of vibration when valves are partially closed in the pipe system. And water hammer. So they're the sorts of things that the meter could experience in the field, and the chamber or the vibration system can mimic some of those.
There's quite a few people who've got sort of meters set up on mobile pumping units. How would they sort of compare the vibrations coming off those with what you're testing there?
So it's a random vibration that we apply. There's 2 types of vibration. There's a sine vibration. There's a random vibration. I can't remember what the acceleration, like the G-force is, but I don't know, I guess it depends on the roads they're driving on and how fast they're driving. But
It's more if they've got a diesel motor on them and they
yeah, yeah. So that's why this is compulsory for those types of meters. Yeah. And then we do a whole lot of electrical testing. This is an area that does our head in, actually. But there's a lot of work that goes behind all this testing, and we adjust the power supply, we vary the power supply, we interrupt the power supply with short-term reductions. We've got a gun that throws 2,000 volts at it, like I think it's supposed to simulate lightning. We overlay voltage spikes onto the power supply. There's all this, yeah, it's quite technical, and fortunately we've got the people in the school of electrical engineering that can do all this testing. But yeah, it's quite detailed and complex. The water quality rig, so Alex mentioned that was one of the ones that they've added in, and the reason why this was added in was there's a potential for mechanical meters to get patent approved and then be put on a system which is supplied with unfiltered water. So there's potential for mechanical meters to get patent approved and then they clog up or they get damaged from elements or particulates that are in unfiltered water. So they've come up with this, sorry about the writing there, they've come up with 3 classes of contaminants. And the first class is very, small fines. Second class is slightly greater fines or larger fines and more concentration of them. And the same with the third, goes up another notch. And then the fourth one, we put fibres in there, so we're simulating weeds in the water. And we're circulating the water, and I came to 100 hours of testing where we turn the water on and off every 30 seconds, so the meter is subjected to 30 seconds of the unfiltered water and then it's off, and so it goes on for 100 hours. So the other disturbance testing is the flow disturbance. So we induce flow disturbances into the pipework. This one, these ones here provide left-hand and right-hand swell generators, so they can twist the water in one direction and twist the water in the other direction. So these are we call this type 1 and type 2. Sorry about that, it should be 2. And the type 3 is a quarter plate, so that simulates a partially closed valve, and these are compulsory flow disturbance tests. The type 1 and 2, so the flow distortion tests, or flow swell generators, they represent 2 pipes out of alignment, so that creates a swell in the pipe, and that's why we've gone with that design, and I think OIML's now switching over to this as well, so you'll find even the domestic meters will have to undergo this testing as well. Just to give you an illustration of what it does to the flow, I was going to put up a video, but I thought I would just show you how far it propagates down the pipeline. It can go for 20, 30 metres for large pipe systems. And so they are quite aggressive, and we've found that mechanical meters don't like it very much. So here's an example of a mechanical meter we're trying to get through, or we're trying to get through patent approval. And in this case here, the meter, the test, so this is our reference meter here, straight pipe. There's the disturbance in the pipeline, and the test meter's 18 metres after the disturbance, and we still couldn't get it to pass. Now, what does pass mean? Pass means that the error without the disturbance and the error after disturbance can't be greater than 1/3 of the maximum permissible error. So the actual meter was still accurate. It was still within plus or minus 2.5%. But because the initial error without the disturbance was, I think it was 0.5 or 0, I can't remember what it was, or close to that number. When we put the disturbance in, it went, I think, to about 1.5%, which meant it failed.
And you just accurate.
Yeah. So, no, it's a really conservative. I mean, The reason why we do this is because you might find any type of condition in the field, and if it can pass this, it'll pass anything in the field. So
So when you're talking about in situ, plus or minus 5%,
yes, if you get a meter that's tested under this condition, yeah, you've got some confidence in the field. It's going to be good. Yeah, that's part of the reason. Alex knows it's quite a tight requirement, but that's the way it is.
buying and selling water, though, isn't it?
Sorry?
That's because they're buying and selling water.
Yeah, well, you're trading. Yeah, trading. So,
Money involved.
yeah. Oh, and we've got instances in South Australia where the resource is limited or it's over allocated, and they're trying to call back some of that allocation.
So that type of meter with a high error at start has got a better chance of passing the test.
Oh, if it was on the right, yeah, if it was out. Oh, but then again, it's a shift. We're talking about a shift. So we're talking about a shift from its initial.
But if it's got a 0.1% error at the start, it's more likely to shift to two-thirds of that than if it started at, say, 1%.
Yeah, well, we're not sure about that. We're not sure about that. Yeah, we're always finding surprises with meters. So how do we get around this issue where this meter can't pass the mandatory testing? In the NMI, there's another clause, or another test condition, which is called installation test, 612, I think it is. And then the meter can nominate the installation which they want their meter to be installed. So when the certificate will have this meter, will only satisfy this type of installation.
And therefore it gets patent approval.
Yeah, yeah. So this will still be in the patent approval to say that for the mandatory testing it was greater than 18 metres and it passed the installation test. Now the installation test allows you to test it and not worry about the difference in error between a straight pipe and the installation. So it goes from quite a really stringent requirement to really a fairly loose requirement. But we have to do all the testing. So this one here is done at a reference flow, which is about 0.7 Q3. This one here is done at all the flows, so Q1, Q2, Q3. Well, it's about 6 flow rates through to Q4. Okay. So here's the type 3 disturbance test. Quite a bit of work involved to set up the testing. So we've got what we call a quarter plate there. And the actual meter, the test meter is located there. This is looking inside the pipe work, so that's the quarter plate, and there's the turbine of the mechanical meter.
How do you verify those flow meters that you're using?
Oh, we've got a reference tank, which is right at the end of the presentation. We've got a reference device, which is a weigh tank, barometric tank. So we do testing on different orientations, so 45 degrees on the up and down positions. Vertical testing, again up and down. This is our reference meter, so it's a 23,000 or 23,000 litre tank with a load cell. And we've got two, we've got a large one and a small one, and that gets our uncertainty down to 0.1. Yeah. So now I'd like to just finish up with a case study which I think demonstrates the importance of patent approval. So this is a case that I was involved in, and it's a situation where an irrigator used used 45% more than he's allowed to. So he's using 40% more than his allocation for the year. And the irrigator disagreed with the water service provider, saying he didn't use it, and somehow they had to resolve what was going on. So the challenge was for the water service provider that he needed to prove the accuracy of the meter in the field. And so what are his options to do that? And so we'll look at it in a moment. But this is the installation. It could be a river, it could be a pond, whatever it is. So you've got an off-take pump, a filter, followed by what we call a dual check valve. And then he's got 12D of straight pipe length and the meter, service meter, another 10D, and then he's got some bends and off to the irrigation system. So that's what the system looks like. In fact, it even had a data logger attached to the meter. So there's a bit more information that we had. So the installation was actually approved by the authority or by the water service provider. It had the minimum requirement of 10D and 5D upstream and downstream of the meter, and it even had a data logger. And it also met the meter's recommendation, manufacturer's recommendation. So for all intents and purposes, the water service provider assumed that installation was appropriate, and the measurements of the water were reliable and accurate. So what are their options? They considered in situ testing, so putting on a clamp on and doing the tests in the field, sending the meter off to an accredited laboratory, having a look at the data from the meter manufacturer, so looking at the specs of the meter manufacturer, see if they could find some information that would tell them that this meter was okay for this particular installation. And they also had some information from the logger which they could look at. So there were a few options they could look at to help strengthen their case. So with the in situ reference meter, the clamp-on meter, there wasn't really much space to fit the clamp-on without that being disturbed. So you really couldn't rely on the results of the clamp-on meter. And the pipe was relatively small. I think they were 80 or 50 mil pipes. And for a 50 mil pipe, if your measurement of the internal pipe or your assumption of what the internal pipe diameter is out by 1 millimetre, well, your error could be out by 10%. So when you get down to small pipes, ultrasonic meters aren't really good. In fact, they had a consultant come by and they had a clamp-on meter and they tested these particular installations and said it was all good. And so it just goes to show you can produce whatever you like in some instances. So the next option, test in an accredited laboratory, that's fine, but they'll only put into a straight pipe length system. They won't put the disturbances upstream of the meter, so you're not really going to find out too much unless the meter is actually out for whatever other reason there might be. And then looking at the meter manufacturer data, which is, we weren't able to get anything from the manufacturer, and secondly, there's a lot of testing done in-house, so how reliable is that information? Looking at the flow data, so we looked at the data from the logger, and we could tell from there that 90% of the water was somewhere between, in this case, just over half a litre, 1 litre per second, up to 2.5, 3 litres per second. So we knew what flow range this meter was operating with. So if we're going to investigate it further, we knew what flow rates to test it at. So the next option was for us to actually set up that whole installation in our laboratory and test it with the actual dual check valve and the same pipe lengths and the actual meter itself, which is what we did. But before we did that, we tested it in a typical rig, flow rig, and we found out the meter was within plus or minus 2.5%. So for all intents and purposes, that meter was accurate. But then when we tested it with the installation configuration, we found out this error. So at the bottom end, it was just outside of 2.5%, and at the top end of the flow range which it operated at was at close to 20% out. And so once we found that out and we presented that information to the lawyers and the barristers, they decided they couldn't proceed with the case. So it just goes to show you can't necessarily pick out whether these meters will operate well under certain conditions. But what this is telling us is if this meter was passed the patent approval test, I'm getting ahead of myself. We'll get on to the next slide.
Was it a mechanical or electrical meter?
It was a mechanical meter. Yeah, it was a mechanical meter. So, question time, and I've raised this in previous presentations. Would have a patent-approved meter used in this installation avoided this dispute? And the answer is not sure. Well, I think yes, and the reason why is if it's a patent-approved meter, it would have passed the mandatory disturbance testing, which is that flow swell generator. So you would have only selected a meter that could have coped with those mandatory disturbance testing, if that was the case. What else could have been done? Well, obviously management of the meter in accordance with the metrological framework. So if you had someone approving the installation according to the framework, they would have realised that the meter wasn't patent approved or didn't have the correct information or certificates. So I think this is before patent approval came in, so perhaps now will change. But certainly it would have saved the water service provider, I don't know how much they spent, would have saved them a lot of money, and even the irrigator would have saved them a lot of money and time as well. So I think, when you see cases like this where the incorrect meter is used or a meter is used that's not patent approval, then you could have these disputes. So that sums up that case study. I'd like to finish up by just saying these are the meters that are either been patent approved or in the process of being patent approved in Australia. So the first two, Crone and Siemens, they've completed their patent approval and they've got their certificate. And then we've got Burmid, Arid, ABB, Rubicon, Burmid, Pentair and Symmetric. So these ones here, Burmid, Arid and ABB and Rubicon are advanced, so they're pretty much, there might be somewhere between 50 and 80% of the patent approval process. And the others have either just commenced or commencing. So before too long, we should have, 3, 6, 9 metres that are patent approved.
And only one mechanical?
Only one mechanical, yeah.
Yep. So the mechanical meter, that'll be really restricted to the installation tests that pass the patent approval process. Yeah.
In reality, this doesn't actually matter about the type of meter as long as it passes the testing that you apply to it.
That's right. Yeah. Yeah. That's right. So I'd like to, finish up just acknowledging Irrigation New Zealand and the sponsors, Crone and Siemens, and obviously the Australian Government for funding the upgrade in our facility. So anyway, there's my contact details if anyone wants to get in touch with me.
Has anybody got any quick questions?
Can I just make a quick comment, Andrew, from a vendor point of view, very quick. Yeah. Taking off my salesperson's hat and putting on my engineer's hat, I think one of the great benefits of NMI is it takes away vendor specsmanship. Okay. Now we all do it. We all put our own spin on our specs. We all do our in-house testing. NMI 10, completely arm's length. So things like your pressure loss, your straight pipe length upstream, downstream, your susceptibility to particulates, all the stuff that we get involved with in a competitive situation, that whole discussion is removed. So end users and scheme operators can say with confidence that there's no glossy bits in there. It's been assessed by a third party. This is how it is. Look at the certificate, and the meter can do this, and this, but it can't do that, and that. So I think from a end user point of view, the NMI 10 patent approval process has got a huge advantage. It makes things a little bit more spicy for us vendors, but at the end of the day, I think it's probably a fairer outcome from an engineering perspective. That's probably that's my comment from it anyway.
Amen.
Just
Yeah, I've got a comment. Just you listen to Alex and listen to James now and you, David, and the one thing that's not answered here is this patent approval is fantastic. We've the day it was put in was fantastic, and then we get a pipe full of, full of crud, no matter what it be.
Yeah.
Patent approval or whatever still isn't going to stop somebody putting their hands on that damn system once every 18 months, 2 years, 5 years, whatever it is, taking it out and checking it and doing some maintenance.
Well, I
So-
agree 100%. The maintenance aspect
It's
is
just I'm
unavoidable.
worried that a lot of people in this room are looking at patent approval as a set and forget.
No, but
That's what I just want to.
Yeah.
the assurance framework document, if you look at that, I think coupled with patent approval, you could have some reliability in
Better reliability,
Yeah,
greater reliability
yeah.
than non-patent approval.
yeah,
Because I think in terms of maintenance too, any engineer knows that a product with no moving parts has less maintenance than one that does.
Yeah, sure.
So although you've got a patent approval for one, let's say mechanical meter, you're going to require more maintenance than a manual meter. That's just a given.
Yeah.
So, but I agree, it's certainly not a panacea for maintenance and good practice, engineering practice.
Yeah.
For example, a manufacturer spec comes out, I'm just going to throw some numbers, says that this meter will be accurate to 5 and 3. When you do the patent testing, you obviously test beyond that. So if it came through patent approval with a 3 and 1, would the 3 and 1 be on the patent approval
Yeah.
certificate?
So what happens is the manufacturers ask us to test at 0D upstream. So we start with 0D. If it passes, we stop there.
Okay.
Yeah.
So
Or we increase the pipe
So you
lengths.
go to where it meets the standard, meets your patent
Yeah.
standard, and that may be more or less than what is
Yeah.
claimed by the manufacturer.
Yeah, so no longer can manufacturers imply that their meters can be installed, let's say 0 and 0 extreme case.
Yeah.
If they can be by NMI, it'll be on the certificate.
Mm.
Clear as day, that's the way it is.
Just a question about the EMC testing you do. Again, taking James's sort of sentiment as well, I represent a vendor. We all get, all instrumentation gets hassled by EMC interference, doesn't matter what it is. And I think probably magnifiers are probably the most susceptible because of the signals they produce. I noticed that your EMC levels are quite high. So usually a lot of these installations are next to nasty, old, often variable speed drives.
Mm.
And they just cause a lot of noise on a property as well. And as the vendors get fingers pointing at us saying your product doesn't work, we send it up to meter services and it checks out 100%.
Yeah.
So I'm wondering if there is any movement in the future to bring those levels of EMC testing to a point which actually interferes with what they experience next to a nasty PSD drive.
Yeah, I think, I know I won't see that happen until a patent approved meter goes out in the field and experiences that problem. So I think, and that will have to go through NMI. So you have to raise that with NMI and they'll then do a revision or work out whether it's an unusual case or whether it's something that could happen.
I mean, electric fence controllers are another classic, as you know, and like you say, variable speed drives, but I don't think, once again, the NMI patent approval is a panacea for good, smart engineering practice. So, you don't run your cables in parallel, high voltage against your mag plate. You do them either randomly or, perpendicular. And you run things through conduits. You put filters on your VSDs, whatever you need to do. That NMI doesn't make these things bulletproof, but it makes them tested at arm's length to as good as they can be and therefore stated. So, but still do your good engineering practice. I mean, for Siemens, for instance, we've got the 0D up, 0D down on our certificate, but you'll also see that we say we still recommend best engineering practice is 5 and 3, or if you guys want to go 10 and 5, that's fine. But if you want to use it at 0 and 0, that's fine, but it's not best engineering practice for lots of good reasons. So you just got to take it with a bit of a grain of salt in that respect. Don't throw away your standards just because you've got a patent approval, because that's going to lead to problems.
Yeah, I think you will find situations in the field which we can't replicate in the laboratory. So,
Okay, I've got one more question, otherwise I'm going to say thank you because I've got some more controversial stuff to get on.
oh good, can't wait.
One more question or not?
All good?
Excellent. Hey, look, James, thank you very much.
No worries.